Valentine, please welcome Valentine from Nanosferix.
Good morning. Thanks for being here. So I'm going to talk about making new materials. Our team has been originally based in Kinatao University of Science and Technology in Saudi Arabia, and we have just transitioned to Case Western University in Cleveland, which is why there is a name change. And we make new materials, and the specific problem that we are trying to solve is making better composite materials. And composites are, of course, incredibly important in modern society. They're incredibly strong, they're incredibly light. You see them everywhere, from airplanes to tanks rockets. A composite material, by definition, is something that is composed of several components. One is the resin, which is usually a thermoset. There is also the fibers, which is something that we see and which is what makes the material recognizable. So everybody can see carbon fiber materials. But there is also a third component that is equally important, and that is a filler. That is something that makes the resin and the fiber stay together. And the most common filler used by industry is silicon. Because it is incredibly cheap, it is something that works well, it is something that can be manufactured in bulk. And it is really the filler of choice. The issue with silica is that it is heavy. So we talk about very standard thermosets such as epoxy resin. Its density is about 1.18, so just a bit heavier than water. Silica is about 2.65. So first of all, the final product is heavier than the resin itself. The second problem is that when these components are mixed, silica starts to settle. And what you see here on this slide is what happens when we mix up the epoxy monomer with commercial silica, and in about a couple of hours, all of it ends up on the bottom of the test tube. And that is a problem if we are trying to make a part with a complex geometry, if we are trying to cure something. So it presents problems with homogeneity. So, and of course the material itself is heavier. So typical silica reinforced composite is about 1.28. So that's quite, it's heavier than epoxy that we start with. So how can we solve this problem? Our solution to this is making hollow silica particles. So specifically, we don't work with silicon dioxide here. We have made a material that is organosilica, so it has some carbon and hydrogen in addition to silicon and oxygen. And we can make those particles in a variety of sizes, in a variety of shell thicknesses. They're nanoscale materials, so they're not, the particles are not very big. And we can modify the chemistry of both the outside and inside of the particle simultaneously. So this is something that no other object I'm aware of can do. So it's an incredibly light material. So here you see pictures of it, but I also brought a jar. So if anybody wants to actually see it, what I have in this jar is maybe 1/10 of an ounce, and it's incredibly light. You can see that it doesn't even go to settle. And it's, despite it being really light, it's a plug-in replacement for conventional silica fillers, because the surface chemistry can be exactly the same as just silicon dioxide. So this is just what I've shown you before, and it's great for making parts with complex geometry. It's great for making lightweight materials. It is chemically compatible with silica. And in terms of our pricing, so our material, the performance of it, is more similar to graphene and 2D nanomaterials, rather than conventional silica filters. So even though we are slightly more expensive than just silicon dioxide, we are way cheaper than graphene, and the advantages are about in the same price range. So we can get adding just 0.1 weight percent of our material to epoxy can lead to a 100% improvement in strength. So there are some articles that were actually made from this material. Indeed, these materials have fairly low density, so we can have quite a bit of it without impacting the weight of the article. So there are multiple applications possible for that, and we are looking, so we have 2 patent applications in the process. We are looking for, and we are looking for partners. Thank you for your attention. So these are some of the companies that we actually had discussions with already, and we're looking for more involvement.
All right, thank you, Valentin. Any questions for him? Go ahead, gentlemen in the back.
Are the materials porous at all?
That's a good question. So the shells are not impervious, so there are holes in them. But it is not a mesoporous material, so you can think of these spheres as smooth shells with a few small holes.
One more question? Go ahead.
What kind of scale would you need to manufacture at to actually be profitable?
That actually depends on the application. So for actually applying this in composites, we are looking at maybe, I would say, 500 kilos a month or something like this. But we are also looking at applications in pigments, paints, pharmaceuticals, cosmetics, and of course, something like cosmetics can be profitable at a fairly small scale because you'll be looking at margins that are like drug. So it's actually very versatile material.
Great. Thank you so much.